All right, today we're going to be talking about the conservation of mechanical energy, and specifically about the law of conservation of mechanical energy. Now, previously we talked about the law of conservation of energy in general, and that is a broad, sweeping law with no exceptions and no conditions. The conservation of mechanical energy, on the other hand, does have conditions and restrictions. And specifically, the law of conservation of mechanical energy states that mechanical energy is conserved in the absence of friction. So this law only applies if there's no friction involved in the situation. And so ME stands for mechanical energy, and this shows that the mechanical energy at time 1 would be equal to the mechanical energy at time 2, assuming that there is no friction involved in the situation. That would occur either on a frictionless surface or a surface with very little friction, or if an object is falling for short distances or at small velocities. Even in real-life situations, we could consider the air resistance to be negligible. So those would be the kind of situations where we would make use of the conservation of mechanical energy. Conservation of mechanical energy is, it oftentimes is more helpful than your kinematic equations because it can be applied in situations with varying accelerations. And so even if the acceleration varies, conservation of mechanical energy still applies. All right, now we've talked about conservation. We've said, okay, mechanical energy is conserved in the absence of friction. However, what makes up mechanical energy? We've talked about kinetic energy, we've talked about potential energy, and it turns out that mechanical energy is actually made up of both kinetic and potential. So your kinetic energy and your potential energy together they form the group known as mechanical energy. So your kinetic energy and your potential energy make up mechanical energy. And it turns out that we actually are talking about two types of potential energy: gravitational potential energy and elastic potential energy. So gravitational potential energy, or GPE, plus elastic potential energy, or EPE, plus kinetic energy, all together make up mechanical energy. So in place of mechanical energy 1, we could actually say, for example, the kinetic energy of the object at time 1 plus the gravitational potential energy of the object at time 1 plus the elastic potential energy of the object at time 1 then would be equal to the KE, the GPE, and the EPE at time 2 as well. All right. And again, that doesn't necessarily have to be at the start and finish of any particular scenario. It could be at any 2 points, that we're wondering about. Let's just say, for example, that that I have a cliff and I have a rock sitting on top of it. All right. Now at this point, you'll remember that GPE is found by multiplying the mass of the object times the strength of the gravitational field, the acceleration due to gravity, times the height of the object above some reference point. So let's just use the ground here as our reference point. And so if we know the height h of our cliff, then we could, and if we knew the mass of the boulder, of the rock, the object, so then we could multiply that together and we could find GPE. And let's just say, just for fun, I'll just make up a number. Let's just say that it's 2,000 joules. All right, so we're going to say that when we calculate m times g times h, it ends up being 2,000 joules. All right, now this object's at rest on the top of a cliff. Remember that kinetic energy is equal to 1/2 times m times v squared. Well, if it's at rest, then its velocity is 0, and so the kinetic energy is 0 as well. So the KE is equal to 0 joules. I'm going to put a slash through that so that it looks like a 0 rather than a delicious breakfast beverage. So there we have it, Ke 0 joules. Now there's nothing elastic here. There's no springs. There's no bungee cords. There's no springs or rubber bands. And so the EPE is also going to be 0 because there's none to consider. And so the sum total of our mechanical energy is in fact then 2,000 joules. Now, if this object then all of a sudden falls off the cliff and begins to fall toward the ground, well, as it falls, its height gets less and less, and so the GPE reduces. It becomes less and less. But also as it's falling, its velocity becomes greater and greater. It accelerates, and specifically it increases in speed. And so even though its height and its GPE are reducing, its velocity and its kinetic energy are increasing. And so as the GPE is actually being transformed. As that decreases, your kinetic energy increases, and they'll increase at the same rate. So as this number goes down, this number will go up, and the sum total of them will still be 2,000 joules at any point along the trip. So no matter where you are along the trip, and even once you reach the ground, before it comes to rest, just as it strikes the ground, the mechanical energy of the object at any given point is in fact still 2,000 joules. All right. Now, if we look at it and consider it at the very bottom, well, the elastic potential energy is still 0 because there's still no springs, bungee cords, or anything else that's taking any of that GPE and transforming it into elastic energy. Now, the GPE, on the other hand, well, now that it is all the way at ground level, its height is 0. And so at this point, since the height is 0, well, if height is 0, then that's going to turn the gravitational potential energy into 0 also. And so both of those are 0, but the total still has to be equal to 2,000 joules. And so at this point, we can know and understand that since both of these are 0, at this point, the kinetic energy must in fact be equal to 2,000 joules. And so conservation of mechanical energy is actually extremely helpful, again, for being able to find how fast something's going, how much height it has, and anything involving GPE, KE, and elastic potential energy. So at this point, some students want to say, oh, okay, so the GPE at the top is equal to the KE at the bottom, so I can just write that GPE is equal to KE, and I can solve things that way. And my answer to you is no, you're clearly outside your mind. Stop. The reason that you cannot write this is because even though in this particular case, the GPE does end up equaling the kinetic energy, it's the GPE at the top at one point and it's equal to the KE at another point. But the only reason that is true is because your other two components of mechanical energy also happen to equal 0. Just the idea that GPE is equal to kinetic energy, there is no basis for that outside of the conservation of mechanical energy. And in order for the GPE at any one point to be equal to the kinetic energy at another point, the other two components of mechanical energy must be equal to 0. And so you really need to start with this fundamental idea that mechanical energy is conserved, and then list those components, and then write in there or substitute in there which ones of those are equal to 0, or if they are not equal to 0, what are they equal to? Okay, so you may not simply start with this assumption. It is not necessarily valid, and even if it is, you have no basis for it if you do not begin with the idea that mechanical energy is conserved. At this point, let's look at an example of a pendulum swinging from its maximum displacement down to the bottom and then back up again on the other side. So we've got a pendulum that's oscillating back and forth, and as it does so without friction, and so the mechanical energy is conserved. And we'll look at a sample of that. Yes. All right. So I'm going to go ahead and draw a reference line. This pendulum, clearly it's swinging through the air. It's above the floor or the earth or some surface that's not drawn in the picture. But we really don't have to measure GPE relative to that surface. We could measure it relative to, say, the lowest point of its swing. And that'll actually be more helpful because that will allow us to set GPE at this point of its swing equal to 0. So that's what we'll do in this case is we'll consider this object as it's swinging from this point to its lowest point. All right. And so we'll start with the idea that mechanical energy is conserved. That is, mechanical energy at point 1 is equal to mechanical energy at point 2. And really, there's no reason why this should be point 1 and that point 2. It's fine to reverse those. Now remember, mechanical energy is made up of GPE plus KE, and I'll put a little subscript of 1, plus EPE. And then that's going to be equal to mechanical energy 2, which will be GPE2 plus KE2 plus EPE2. All right. And so, now, if we consider that this is the highest point of the swing, at that point it will be at rest. And so its kinetic energy at that point would be 0. Now, the elastic potential energy, of course, is 0 in both cases because there's nothing in the question or what I've told you to indicate that there's any kind of elastic potential energy being stored, no work being done against any elastic devices. Now, if we're taking this dashed line to be the reference point, then its height at that point is 0, which means the gravitational potential energy at that point is equal to 0. Now, it does have some kinetic energy because it's swinging at that point. It has some velocity, so we don't, in fact, know the value for that yet. And as I mentioned earlier, the EP at that point is 0. So we see that GPE at point 1 is equal to KE at point 2. And then you could take GPE and set it equal to M times G times H. And the kinetic energy, in fact, we could find as 1/2 times M times V squared. And then if you knew the mass and the height, you could solve for the velocity, or if you knew the velocity at the lowest point along with the mass, you could solve for the height at the highest point, depending on what other information you had. Some of you will notice that there is actually mass in all of our terms at this point, and so we actually could divide the mass out and simply set GH equal to 1/2 V squared. I'll not, in fact, do that at this point, but if you notice that and that makes sense to you, you can do that in some situations. Now, that only works to solve. That only works if you're solving for something else. If you're actually asked to solve for the value of GPE, then of course you would need to include the mass. You could not just discard it. So let's see, first of all, let me, that looks a little bit like a minus. I want everybody to remember that that is in fact a multiplication. All right, and a situation where you might use this would be, let's just say that you were told that its velocity at the bottom of the swing of a pendulum was 5 meters per second. And maybe you're told that it has a mass of 1 kilogram. And you were asked what is the maximum height that it reaches above the lowest point of its swing. All right, and so you say, well, I can find height from gravitational potential energy, and I'm given the mass and the velocity. And so then you could put in 1/2 times the mass times the velocity squared. And it looks like that's going to come out to be around 12.5. And then that would be equal to M times 9.8 times H. And so at that point, 9.8 H would be equal to 12.5, and so you'd make you would do the division and see that it's going to reach around 1.3 meters. I don't have a calculator right here in front of me, but I'll let you do the math and find out exactly what h is, and it should be around 1.3 meters. Let's look at one more example. And in this case, we're going to have an object that I'm going to drop, and we're going to have some elastic potential energy involved this time. So again, let's just say that we have a 1 kilogram object. And let's say that we have a spring that has a relaxed length of 40 centimeters. So I'll just go ahead and convert that to 0.40 meters. All right, and so let's say that the object is being held at rest with the spring at a relaxed length of 40 centimeters, and that it's released from that point and falls an additional 25 centimeters. So that'll be 0.25 meters. And let's say then that you're asked. I'll tell you what. Let's just say that we're asked to solve for k. That we're asked to solve for the spring constant at that point. Let's see if I've given us enough information to solve that. And so again, we would say, all right, the mechanical energy at point 1 is equal to the mechanical energy at point 2. And the mechanical energy at this point is equal to, we're going to have the sum of the GPE plus the EPE plus the KE, and all those are at point 1, and then that'll be equal to GPE plus EPE plus KE at point 2. Now you remember that a minute ago I said that the object was at rest when it was being held here at its top position, and so that tells us that the kinetic energy would be 0. And then at its lowest point, well, that's where the spring has stretched all the way out. It's come to rest just before it begins to oscillate back up, and so once again, the kinetic energy will be 0 at that point as well. If you can select points to work with where one or more of your values are equal to 0, that's just really helpful because it allows you to eliminate some components from consideration. So with that in mind, I'm actually going to choose my reference line to be right here. And if I choose that for my reference point, then we can say that the GPE at the lowest point is also equal to 0. And so then I'll have the idea that all of the mechanical energy then is in the form of the elastic potential energy. Now, the elastic potential energy here, remember, if the spring is at its relaxed length, then we don't have any elastic potential energy. The only time we have elastic potential energy is when the spring is being stretched or compressed. So we can put the elastic potential energy as 0, which means that all of our mechanical energy is equal to the gravitational potential energy. All right, so at this point then, remember that the gravitational potential energy is m times g, the mass times the acceleration due to gravity times the height. And the elastic potential energy is equal to 1/2 times k, the spring constant, times x squared, where x is the distance compressed or stretched. All right, now let's see, we once again have a 1 kilogram mass. Thank you very much for giving us that. We know that g is equal to 9.8 since we weren't told anything about this being on an additional planet. And we know that it is 0.25 meters above the reference line. And so at that point we have enough information to solve for the GPE. And that's going to be equal to 1/2 times k, and that's what I said that we were going to be asked for. We were going to be asked for the spring constant. And then x is, well, if this falls 0.25 meters, then that means that the spring must be stretched out 0.25 meters from its relaxed length. And so then 0.25, and that, of course, will be squared. from our formula 1/2 kx squared. And once again, at that point, we can multiply that out, multiply by 1/2, and then do the division in order to solve for k. And we'll be victorious in that quest. Remember that the units for k, the units are newtons per meter, because it's talking about how many newtons it takes to stretch a spring 1 meter. All right, I hope that's helpful, and that will give you some basic understanding of the idea of conservation of mechanical energy. You thought we were done? Not quite yet. Question came up, so what's the point 4 about? Well, it turns out that the point 4 I told you is the relaxed length of the spring. What if instead of being told that it had fallen 0.25 meters, what if you were told that it fell until the spring was at a length of 0.65? Well, in that case, you would have needed to say to yourself, ooh, now it's at a stretched length of 0.65, it had a relaxed length of 0.40, and then you would actually have to do some subtraction in order to find out, hey, that means it's fallen 0.25, and that is not only how far the spring has been stretched, but also ends up being our change in height. And so then again, that allows you to set a reference point and find GPE from that. All right. Thanks very much.